Hello, everyone. Hope you can hear me. Kostis, if you can just let me know if the sound is good.
It's perfect.
Okay, good. So hello again. Welcome to another Connection Wednesday webinar. My name is Theodore. I'm the director of StatiCa UK, and together with Kostis, our support manager, we're going to present you today's content. Actually, Kostis is going to do most of the work. My part is a bit smaller. Before we start the presentation, I just wanted to mention the usual information about GoToWebinar for anyone who hasn't used it before. So in the right side of your screen, you will see a control panel, and you can use that to enter any questions you might have during the webinar. We will answering these questions as we go along, and we will probably have some time in the end. So don't hesitate to send anything you want using the questions tab. So I'll just go very quickly about through today's agenda. So as usual, in the first part, we're going to show a customer project, and today we're really excited to show one of the Mott MacDonald's project. It's the Waterloo Station upgrade program. I'm going to say a few words about that later on. In the second part, we have the HelpDesk highlight as usual, and today we're going to talk about backing plates, something that we receive very often in our HelpDesk. And of course, in the third part, I suppose that we will have some time for questions. So we will try to answer as much as possible. If we don't manage to answer all of them, we will try to do that through an email after the webinar. So let's start our presentation with the customer project, which comes for Mott MacDonald, as I mentioned. And this was actually presented in our User Day conference in London about a month ago. One of the latest projects that Mott MacDonald were involved is the London's Waterloo Station expansion project. It's actually called Waterloo Station Wessex Capacity Alliance, which will be completed in 2019, and will provide a full design and construction to bring the Waterloo International Terminal back into use, but also some modifications and improvements to the existing station and the rail systems. Mott MacDonald were the designers for the steel frame of this infill roof, while Born Steel were the steel contractor carrying out the work. So we're really excited that Born Steel, also a user of StatiCa, and Mott MacDonald were involved in this really nice project. As the connections and the frame had a high degree of interaction in terms of structural behavior, it was decided that part of the MacDonald team would be seconded to Born Steel to facilitate the coordination of the connection and primary steelwork design. In this slide, you can see a complete 3D model which shows both the existing structure and the new one. And the connection that we're going to focus on today is located in the west facade, as you can see here. So this is in the center. This is the connection that we're going to show. In this slide, you can see actually the connection that we're going to model. This was a very complex connection, and there were quite a few challenges involved. It comprises a vertical wind truss formed from RHS outer cord, a CHS inner cord, and lacing elements. And attached to this are 4 MacAlloy tension rods and 2 RHS transoms. You can see also in the slide the design requirements, the performance requirements. As you can see, there are quite a few. This connection was architecturally exposed. It should have a 120-year design life, access holes for bolt tightening, 3 different sets of load combinations, ULS, blast, and post-blast, and so on. A lot of challenges, and one additional challenge to that was the stiffness requirements for the transoms. So as the connections were required to be axial stiff and fixed in the major axis, while pinned in the minor axis, Mott MacDonald looked at various options, trying to balance the design requirements with buildability and, of course, fabrication time. Now, using idea StatiCa, Mott MacDonald was able to assess the stiffness of these options to come up with a balanced solution. So I don't want to go in any further details, because the most important thing is to actually show how we can model this connection. And with this, I'm going to switch to Kostis, so he can show you a live demonstration of this connection. So Kostis, I'm going to give you the presenter.
Okay, so hello everybody. Theodore, can you confirm that you can hear my sound and see my screen?
Yes, sound is perfect. The screen, we cannot see it yet.
Okay. Is everything okay with the screen?
Now, yes. Now we can see your screen. Perfect.
Okay, so let's start to model this connection. I will start from scratch. Since this is not a typical connection, I will use the Eurocode, and I will go with a steel grid of S275. Let's go and create the project. And let's start by adding the column. For this, I will add a new member. This will be a square hollow section of RHS 200 by 150 and 5 mils thick. I will rename this to C. I will change its inclination to 90 degrees and its geometrical type to continuous. Then I will add a beam of the same cross section. I will change its name to B1. This beam will be ended. It will have 0 inclination. I will rotate it, and last I will also rotate it around its axis. So for this webinar, I will be introducing each new member and then connecting it to cope with the complexity of this connection. So now that we have introduced beam B1, I will connect it with a stub operation. I will use an M12 bolt of 8.8. I will set the stub to be at the beam B1 and change the position of the plate-to-plate connection. I will leave its thickness to 10 millimeter, modify the geometry of the plates, move my view, and then define my bolt positions. I will also set my welds and set their throat thickness to 4 mils. I will return to the previous view, and I will also change the type of the stub to another member type. I want this to be compatible with the size of B1, of member B1 and the square hollow section. So I will introduce an IPE section of 200 millimeters. The next step is to introduce an access hole at beam B1. I will use the opening operation. I will set my operation to be at beam B1 and then change the geometry of the hole. I will set it to rectangular. I will also add some rounding to the hole and then move it slightly to be closer to the plate-to-plate connection. Last, I have to weld my stub at my column. So I want to weld this stub on this column, and I will use the surface cutting method. Again, I will change my welds to double fillets and set the throat thickness of this operation. The connection of beam B1 is ready, and now we can move at the opposite side. So let's copy member B1, rename it, change its orientation, and the only thing I have to do is copy the rest of the operations. So let's copy stub 1, change the member. Let's copy the opening and select the position of the opening. And last, let's copy the welding of the stub on the column. And the beams are in place. Next, we have to create our diagonals. I will add the first diagonal, rename it. I will switch my view to transparent to be able to spot my diagonal. And change its cross section. Since we want to model MacAlloy bars, which are typical, we will not use the rod operation, but I will use a general tube cross section to approximate the rod. Let me rotate it a little bit. And since we want to connect it with a single bolt, I will change its model type to this one. So let's start connecting our rod. I will add a clip operation. Let's relate this clip operation with our diagonal. Then we have to move the connection a little bit. And then we will set the geometry of this connection. Let's rotate the view a little bit. Zoom in. We will change this to a double cup plate. The cup plate shape will be circular. And then I will define the geometry. And of course, let's change the cup plate size. let's look again from the side. Now that we have enough space, I can go and define my bolt, an M36. And then I will add a little rounding at my tongues. For this, I will use my editor. I will introduce some rounding with a value of 55 mils, and it will be at corners 1 and 2. Now this is what I want to apply in my model. Let's test it. It's okay. So I accept the changes and move on. Now let's move the gusset in place. Change its thickness. Move it by 150 mils, and then increase its size a little bit. Now the gusset is in place, and I will start modifying its geometry. Let's zoom in a little bit. I will add a cut-off plate operation, and I will cut my gusset. And for the cutting, I will use the circular cap plate. Now let's look again from the side. The software uses the cap plate to cut the gusset, but it creates a connection which I will deactivate and add an offset of 10 mils. Last, I will use the editor on my gusset to add a bevel. Let's define the size of this bevel. I will apply it at this corner, and let's test it. It's okay, so I accept the changes. Now the connection of this diagonal is okay, so let's start to add the rest of the diagonals. I will copy this one, rename it, change its inclination, and then I will start to copy the previous operations. So let's copy the clip operation. This will be copied on the second diagonal. Let's move the gusset a little bit, and then we will have to change the position of the bevel. Let's test it on the model first. It's okay, and we accept the changes. I will also copy the cut-off plate operation, and I will use the cap plate to cut the gusset. The second diagonal is there. So again, let's copy the first diagonal, rename it, change its direction. So this time I will copy the clip operation from the first diagonal, apply it on the third one. Again, copy the cut operation, modify this gusset with this cap plate. The diagonal is connected. And last, let's add the fourth diagonal. I will copy the clip operation. and again the cut operation, modify the gusset, I'm sorry, with this cap plate. Our connection is almost there. Let me change back to my solid view. And last, I have to add a new member. This will be of a circular cross section. Let's change its direction and its inclination. And to connect this member, I will use a cut operation. So I'm connecting member M8. I will change this to surface, and the connection is ready to be loaded. Since this is quite complex, I have prepared an Excel sheet to load my connection. I will activate the loads in equilibrium. Let's select the loads. Import the loads, press OK. So the connection is ready to be solved. So let's calculate it. And since this takes some time, I will jump to the already calculated connection, which is this one. So what we see here is after the solution is over, we see the overall check, which shows what happens to each member of the connection. We have gray areas for low stressed members, green areas for average stress levels, orange for members whose utilization is close to the limit, and red for failing parts. Of course, there are no failing parts in this connection. We also have an overview of the solution at the top left window here. We can see that the analysis is 100%, which means that all loads were successfully applied during the solution of the connection. We see that all our plates are below the plastic strain limit. All bolts are utilized below their limit. All welds are utilized below their limit. And we can see also the result from buckling analysis. If you want to go into depth and check the results, you can go at the Check tab. And here we have the Analysis tab. Again, this shows that for this cross-section, all loads were applied. We can see a table of all plates in our connection. So for example, if I select my column, at the bottom, I can see the unfolded column and the visual representation of the checks. This is the same for every plate or member in my connection. Then we can see a table of our bolts. So you can see each bolt in the model. Let me just change my view to solid. So for example, if I select Sorry, let me go with the strain check. Okay, so if I select, let's say, this bolt, I can see the plate that this bolt, the plate this bolt belongs to. I can see the bolt highlighted with a black color. Here, we can see the critical load case. We can see the tensile load, shear loads. We can see the bearing resistance of the plates and the utilization in tension, utilization in shear, and the utilization in interaction of tension and shear. We also have our welds in the same tabular format. So if you select one weld, we see, let me change back to undeformed shape. Okay, now let's select this one. We can see the position of the weld highlighted with an orange color. And the relevant stresses. And of course, I can expand my table and see the code checks and the formulas. Last, we have the backlink, the results from backlink, where we can see backlink shape for the critical load factor. Okay, it takes some time. And we can also see it deformed. So this is it from my side. Let me return the presenter back to Theodore. So Theodore, I'm giving you the presenter.
Okay. Yep. Thank you. All right. I suppose if you can see my screen now. So thank you very much for that. So next is the help desk highlight. So as I mentioned earlier, today we're going to discuss about packing plates, and we will show what are the good practices, how to use them, and what are the examples. So just a few words about packing plates. So the main purpose of packing plates, which are sometimes they're called filler plates as well, is to fill the gap between a steel structural connection. So and it's only applied to bolted connections. So as you can see in this picture, when, for example, we have a splice where the cross section is changing, then we're using these packing plates to fill the gap. This can be also in a column, let's say. So various examples, various use of these packing plates. And or for example, in this, as you can see on the right side, in a connecting element, we can use this when we're trying to connect two elements that have a different thickness. Now the maximum step, as the code says, between two adjacent surfaces should not exceed the 2 millimeters. I think there is a mistake in the text there. It should say shouldn't exceed. So if you have a higher distance, a higher step of 2 millimeters, then you have to use a packing plate. Now, some of the applications of that is, as I mentioned, it can be in a splice, which is the one that we're going to show you today, or it can be in a situation where you have to create some eccentricity in your beam. So as you can see, this diagonal, in this diagonal, we needed to have a small eccentricity from the connecting plate, so we can use these packing plates there. So I will switch over again to Costis to show you how we can model this splice and by using the packing plates, and what are the some tips, let's say, how to use them more effectively. So I will give you back the presenter, Costis. Your sound is still on, as I see.
Okay. Okay.
Good.
Thank you, Theodore. Just confirm that you can see
we can
screen.
see it. Yeah, we can see it.
Okay, so this is the connection from our help desk. Here you can see that a user is trying to splice two beams with different heights. And for this, he's using packing plates. I'm touching them just to highlight them and show you their position. So what is the problem? The connection is seemingly okay, but if I press calculate, the software gives me this error that the bolts are too close to plate edge or outside the connected plate. And this goes to this manufacturing operation. Now let's investigate a little bit to see what happens. When I select this manufacturing operation, I can see here that the bolt grid manufacturing operation is highlighting the connected plates. Now I can see that first thing I can see is that the flange of beam B1 is not highlighted. Okay. Now let's try to increase the items count to 4, and then let's select the members one by one again. So I will select this member, this member, okay, the flange of the beam, and this is SPL1B. Okay, so now that we fixed this grid operation, let's calculate again. Okay, but we see that the problem persists. Okay, one hint when you investigate these problems is to go at the BOM, where the software is trying to show what happens. So you can still hear that we have some bolts outside, defined outside of the backing plate. Now let's go back in our design here, and we can see that the splice operation that was used by the user is creating backing plates. Now the grid operation here is creating bolts, but if we look at the other side, we see that this backing plate is not connected. So this is an indication that we need two different grid operations to perform the connection correctly. So let's define the position of this grid operation, copy it. And this time we will change, we will select the correct backing plate, change the position of the bolts, and there it is. Now let's try to calculate again. Okay, the software is warning us for a different position. This time here we have the same, exactly the same problem. So okay, so let's see, it's this operation. Okay, so let's start copying our operations here. Again, we will define bolt grid, Okay, I see we're also missing a plate. So let's copy this one. And we will use the SPL2A plate as a doubler. Let's move it to the front. Again, let's try to copy this operation. Let's select the connecting plates. Now we have to copy this on the other side. And move our bolts here. The other thing we see is another minor problem, is this splice here. I just have to change the way it is defined. And I will copy the splice on member B1. I will set it to be connected to an existing plate. So the connection is finally calculating. So with this, I conclude my presentation on this help desk item. I will give the presenter back to Theodore, and we will move on to any questions you may have.
Okay, thank you, Kostis.
Just a minute to give you the presenter.
Okay, so if you have any questions, I think we have pretty much answered many of the questions that you have sent us during the webinar. I see that there are a couple of questions here. Let me just check if there is anything that it is not answered. I see. No, I think that we have pretty much answered everything. So I don't see any new question coming up. So I think we can move on. So just for those of you who haven't used the software yet, I would strongly recommend to download the free trial. We have a 2 weeks trial version that you can use, and you can make your own, let's say, tests and verifications. So you can download it directly from our website, ideastatica.com free trial. So go ahead and do this. If you haven't used the software, I'm sure that you will find this very, very interesting. With this, I think we can conclude. So the next connection Wednesday will be on the 14th of November. That is in 2 weeks. The registration link is already on our website, so you can immediately register for the next webinar. Now, after the webinar, you will receive, as always, the recording. So in the next couple of days, we will upload the recording of this webinar, so you can watch it again if you want. And if you have, of course, if there are any questions, just send it to us through email. If you are also a user and you would like to show one of your projects in a next webinar, you can also send it to us at helpdesk@ideastatica.com. And I think with this, we can close this webinar. So thank you very much for participating. And we certainly hope that we will see you again in the next one. Thank you. Bye-bye.
Bye.